Hello. So let's just continue with the 8086 architecture. So I've already drawn the architecture diagram. Now let's go through it. So we have seen this complete 8086 architecture is divided into two parts as shown by this dashed line. So these two parts are, first part is BIU, that is bus interface unit, and the other is the EU, that is execution unit. Now, this BIU contains the memory interface, instruction queue, the list of instructions which need to be executed. A control system is there which is shared between BIU and EU. All these segments, extra segment, code segments, stack segment, data segment, and instruction pointer, these are part of BIU. And the registers, accumulator AX, BX, CX, TX, stack pointer, base pointer, source index, destination index, these all are part of execution unit. Also, execution unit contains ALU, that is arithmetic logic unit, as well as the operands and flags. So overall, this BIU performs the bus operations, that is instruction fetching from instruction queue, reading and writing operands for memory, and calculating the addresses of memory operands. Basically, the instruction bytes are transferred to the instruction queue, and execution unit executes instructions from the instruction system byte queue. And important thing is that both these units are operate asynchronously in a asynchronous manner. That means the clock of both these units are different, and this allows 8086 microprocessor to have an overlapping instruction fetch and execution mechanism. For example, if I have instruction 1 as fetched and instruction 2 as executed at the same time, this is being fetched and this is being executed at the same time. This is called as pipelining, and this is very important for achieving high efficient computations. This diagram represents signal groups of 8086 microprocessor. We have VCC, ground, and clock pin. Then we have mode pin, which enables minimum or maximum mode. Then we have this memory input output. This is basically a status line logically equivalent to S2 in maximum mode. When it is low, it indicates the CPU is having an input output operation. That means for 0, it means input output operations, and for 1, it means memory operation. Then we have INTA. This is interrupt acknowledge. This is interrupt acknowledge. So interrupt acknowledged signal is used as a read strobe for interrupt acknowledged cycles. That is, when it goes low, it means that the processor has accepted the interrupt. It means when it is 0, that means processor has accepted the interrupt. Then we have ALE. This is address latch enable. This output signal indicates the availability of valid address on address and data lines, and it is connected to latch enable input of latches. That means the signal is active high and is never high stated. Then we have this data transmit receive. This output is used to decide the direction of data flow through the transceivers, that is bidirectional buffers. When the processor sends out data, the signal is high. That means this is high for out data and low for in data. Then we have DEN, data enable. This signal indicates the availability of valid data over the address data lines. It is used to enable the transceivers to separate the data from the multiplexed address and data signal. Then we have hold and hold acknowledge signal. When the hold signal goes high, means when the hold signal is high, it means that some other master processor is requesting the bus access. Therefore, the processor, after receiving the hold request, issues the hold acknowledge signal on HLDA pin. This is hold acknowledge pin. At the same time, the processor floats the local bus and control lines. When the processor detects the hold line low, it lowers the HLDA line. Hold is asynchronous input and it should be externally synchronized. Then we have S3 to S0, S2, S1 and S0 are status line. S2, S1 and S0 are status line, and they reflect the type of operation being carried out by the processor. Now there is a S2, S1 and S0. Depending on the configuration of these, the operation is basically decided what operation is performed by the processor. So 3 zeros indicate interrupt acknowledge. Then 001 indicates read input output port. 010 indicates write input output port. 011 means halt. 100 means code access. 101 means read memory. 110 means write memory. 111 means passive, that is, it is not used. One important thing, this is BHE, this is bank high enable signal, bank high enable signal. Now, logic 0 on this is used as a memory enable signal for most significant byte of half of the data, that is D1 to D8. D1 to D8. We will see into this is interrupt request and this is interrupt acknowledge signal. So interrupt request is an input. Interrupt request is an input to 8086 processor that can be used by external devices to signal that it needs to be serviced. That means if INTR, this add signal is at logic 1, that means active interrupt request. And when the interrupt request has been recognized, it indicates the fact to external circuit. That means logic 0 can be placed at INTA output. So this is interrupt request and this is interrupt acknowledge. Then we have test. Test input is also related to external interrupt interface. Execution of wait instruction causes 8086 to check the logic level at the test input. Then we have non-maskable interrupt, and reset interrupt. We will see more details about interrupts and programming in the next lecture. Thank you.